Dr. Cassidy has been the instructor of soil science at Oregon State University for over 20 years. That's a lot of dirt. The introductory class now has over 100 students each term and is very popular. Dr. Cassidy is also the founder and faculty advisor for the wildly popular OSU Organic Growers Club. You know, your local soil and water conservation district here, the Ciudad district, I worked for them for 11 years, and they got that mill levy passed, so they're able to do a lot more than they ever have done before in serving our people with agriculture and farming and ranching and whatever the case may be. And it's very important that they got that. And their phone number, by the way, is 510-DIRT. You get it? Yeah, that's their phone number. That's their phone number. Okay. Anyway, and Dr. Cassidy is coming from a non-traditional background, music, for over 40 years. What do you play, the harmonica? Okay, the harmonica, anyway. And he's passionate about soil and is popular with his students because of his dynamic speaking style. Yay. Okay, the Student Farm Project has over 300 student volunteers on its list, serve, and continues to grow. Over 25,000 students have participated in the farm's program. The farm is largely self-supported through purchase, state sales, and cultivates over 50 different kinds of fruit and vegetable crops, and is just beginning its 25th season. Please welcome Dr. James Cassidy.
This thing on? All right. Man. Jeez, I guess I'm old, is what that means. Hey, everybody. Good morning, class. It's 8 o'clock in the morning. Hope you're up for it. I have to show you this picture. These are just some vegetables, just to gain some credibility. I do grow things in the soil. I've been teaching. Running this student farm has really been the work of my life. Just changed my life. I'm still in the music business, but I quit the music business in 1993. We'll talk about that later if you want to, whatevs. And I just decided to do something real. And so I ended up in soil because I was interested in fish. Go figure that out. We'll get there. But I've been teaching soil science for 20 years, and it's just transformed my life, I'll tell you that. This is just a picture of some vegetables. The student farm is self-supported through the sale of fruit and vegetables, and so we have a CSA program, and this is just a typical weekly box that our customers get. We do 30 weeks of vegetables that they pick up from where we produce them. The reason they look pretty nice here because there's at least 25 different things on there, and it took me 25 years to learn how to grow these because each one of them I had to figure out and fail for many years. But anyway, just wanted to do that. It's all about soil. And I don't just mean like vegetables or even trees for that matter. I mean everything. It's all about soil. Maybe you've never really thought about this before, but every atom in your body has been through the soil system billions of times already. Every atom. In fact, every atom in your body was once inside of a rock. And rocks dissolve in water. We'll get to all that in a minute here. And I mean, everything you ever will see, everything you will ever see, every person you ever see, all of it is going back to the soil pretty soon, actually. I mean, it's almost over, folks. And I don't mean this talk. I mean your life. It's like a flash. I mean, most of the time, you're like soil underneath, and you're like, hey, this is pretty cool. Before you know it, it's over. So I hope you're having a good time, because it's almost over. And yet, here we are together, all of us, like 400 people or whatever, and a bunch of people online, together at this moment in the history of the cosmos, at this particular moment in the history of the cosmos, where we actually know stuff about, what's going on a little bit. We know how stuff works. We believe in CO2 because even though it was invisible and stuff like that, we know what stars are made of and where things really go. I mean, it's a miraculous time to be alive. And for us to be together at this moment, it's sacred, man. I'm telling you, it's pretty good. So, I don't know if you know, I don't even know if you know this, but you are a habitat. What soil is a habitat. We'll get there. We'll get to all that in just a second. But a single pinch of soil, I actually happen to have some soil. It was pretty hard to find. Actually, it's not hard to find. I went outside of this building, and I went off to where it was just like nowhere out there. And it's pretty sandy, I'll tell you that. And here's a little pinch of soil. Right, hey, way in the back row. Pinch of soil here. Just kidding. Really, it's here. I'll come back there. In a single, get your head around this. In a single pinch of soil, there are over 1 billion living organisms. In this particular pinch of soil, in this one, in this one, in any pinch of soil you ever will encounter the rest of your life, and I dare you to remember this, I dare you to forget this. In a single pinch of soil, there's over 1 billion living organisms. And not just a billion of one thing. Literally tens of thousands of different species are in here right now. 99.99% of which we don't even really know who they are or what they're doing, because they're just so small and there's so many different kinds. And with the DNA technologies coming down in price and all that stuff, maybe know about 0.1% of what those are and what they're doing. But most of them we don't, and yet we know they're there. We can measure them. We can measure their functions. And that's just mind-boggling. What they're doing is they're making this all possible. And we'll get to all that in a little bit here. But I just want you to at least the concept of that. So I have a picture here I want to show you. I just threw this together. I'm sure you've seen these kinds of monographs before, back when they actually drew things in books and stuff. And, I'm not an expert at trees, but I do know about growing plants, and we're going to talk a lot about how plants work here. But look at this image, and you can see that so much of the plant is underground. For some plants, like grasses, most of the plant is underground. And all, of course, you know about trees, and some are very deep and rooted and some aren't. But I just thought what we would do is we just kind of look at it from a different perspective. My sliders, oops, not that one. Oh, is it not going to work? Okay, I don't know what happened to that. It did have a nice upside down image. Now, who cares? So we're going to talk about what's going on under here, because this is the habitat. And soil is habitat. If you get nothing else out of this talk, if you can conceptualize the idea that soil is habitat, by any measure, the most diverse habitat on the planet Earth is underground. Sheer numbers of organisms, diversity of organisms, mass of organisms. The mass, just the sheer mass of organisms that live underground far exceed that what's above ground. And most people are like, well, what about the oceans? Aren't they like super diverse and stuff like that? It's like, yeah, kinda. Sure, in aggregate, but you take a cubic centimeter of ocean water, and everywhere in there is about the same wetness. It's wet. And everywhere in there is about the same temperature, about the same pH, about the same nutrient distribution. It's not that diverse. It might be super awesome for certain life forms, but in a cubic centimeter of soil, there are just massively different habitats with different chemistries and different pHs and different anaerobic. For one thing, there's air in soil, spaces for air. That's twice as many habitats as the ocean right there. And really small pores can be captured and cemented in and can be these extremely low oxygen environments, and other places are lots of oxygen. So really, really diverse habitat. And the diversity of the habitat begets the diversity of the organisms. And the diversity of organisms begets the diversity of the function and redundancy of function. And the redundancy of function allows for this to happen. The functions, the services that those microbes that are providing for this organism to live there. So soil is habitat. A single pinch of it contains over 1 billion living organisms. And what soil is like rotted rock. Most of you kind of conceptualize that it's somehow minerals or something. And I happen to have a rock in my pocket right here, just in case. Here it is. It's a rock. I'll bring it over there. Even from, the 5th row or the 10th row here, you can see that there's these big black crystals in here, and there's red crystals in here. And what a rock is just a bunch of chemicals. And the individual crystals that you can see in the rock are just different minerals, which are just made out of what everything's made out of. The periodic table of elements. These are elements in a chemical form that are relatively stable. And this rock, that's what everything's made out of. There's 118 elements in the periodic table, depending on which ones you count, the other ones that last a billionth of a second or not, or whatever. But that's what everything is made out of. Everything in this room was either mined or it was grown, and it all comes from rocks. And in this, these different crystals, and rocks dissolve in water. And if you don't believe me, at lunch today, hey, you want to know what the answer is? Doesn't matter what the question is. Do you want to know what the answer is? The answer is add organic matter. What's the answer? One more time. My work is done. Add organic matter. Because what organic matter is, we're going to talk about in a second, is energy and carbon and nutrients. And so at lunch today, when you're adding organic matter, I want you to take a little bit of table salt and put it in your hand, and that is a mineral called sodium chloride. And that's a mineral that dissolves very fast, and you can tell because you can lick it. And it's a mineral that dissolves almost instantaneously. I mean, in geologic time, instantaneously. And the first thing to dissolve out of a rock are the salts. And some minerals dissolve fast, and some minerals dissolve slow. And salts are the ones that dissolve first. And I'm going to do a little demo. Can I just borrow that cup of water just for a second? Ready for this? I'm going to pour this water on this rock. You ready? Everybody looking at the rock? Boom. You see that? I'll do it again, just in case you missed it. Whoa. See that? Really, a little bit of that rock just dissolved. Really. It's being attacked by hydrogen ions, and it's weakening the structure of those crystals. And a little bit, and the first thing to dissolve out of the what? And a little bit of salt just dissolved out of here, and in the water, and it went down to that carpet. And now it's there. It's going to dry out, and it's going to reprecipitate out as a salt crystal. And then they're going to run some machine over this and vacuum it up with water and scrub it, and that's going to go in the thing. It's going to go in the drain. They're going to dump it down. Eventually, it's going to end up in the river or something. And that little bit of salt, or say if we did it outside, it would go into the soil. And every time it rained, it would go down a little deeper and dissolve and go down a little deeper. And pretty soon it would get to the water table, which is connected to the river. And the little river is connected to the bigger river, and the big river goes all the way, and then it eventually ends up in the ocean. And that's why the oceans are salty. Because the salts dissolve off the land and end up in the ocean. And the next thing to dissolve out is the molybdenum, and the calcium, and the phosphorus, and the potassium, and all the other things that we call nutrients. That's what nutrients are. They dissolve out of the rock, and they end up in the environment. And so the next thing to dissolve is the molybdenum and the potassium, the phosphorus, and all that stuff, and the iron. Eventually, this thing will completely dissolve away. I mean, rocks are very unstable at the surface of the earth. They're very stable underneath, deep down at high pressures and high temperatures where they were made. The chemical environment there was such that those crystals could form at high temperatures and high pressures. And then it comes up to the surface by some means, either volcanic or plutons or some erosion or uplift or something like that. And they're actually super unstable at the surface of the earth because they don't have the pressure and the heat to hold them. And all of a sudden there's this liquid water and they're falling apart rapidly. And so the next thing to dissolve out are these other nutrients. Where do they end up? In the ocean. And that's why there's sharks. Because that diffuse nutrient bath is out there, and there are these phytoplankton that use the energy of the sun to harvest them and to build their little tissues and then build their little cells. I mean, what is a cell made out of, right? Like the nuclear membrane and all that's made mostly out of a phospholipid bilayer, which is phosphorus. And where did the phosphorus come from? A rock that dissolved out. And so then there's a little zooplankton that eats the phytoplankton, and then there's a little fish that eats the zooplankton, and then there's a bigger fish that eats that, and pretty soon it's a shark. And that's how it works. That's how life is on this planet in aquatic systems. But the same environments exist inside of soil, just in these tiny little spaces where there's water hills. Thank you so much. Appreciate that. And so that's, what's happening. So all of the nutrients are dissolving off the land, but because of soil, they're kind of temporarily held in these little tiny pores inside of the soil where they can have nutrients. And that's what nutrients are. And every atom in your body was once inside of a rock that dissolved out and was taken up by a plant. And then you ate the plant because you added organic matter, and then you digested it and it was released. You either ate the plant or you ate an animal that ate a plant, or your mom did. And that's why we're all here. Really, that is a fact. Those are facts. And every atom in your body, sooner or later, pretty soon, is going to go back to that whole system, as it has done billions of times already. Treat all this whole building, whatever it's made out of, sooner or later they're going to tear this building down, and a little bit of salt that's still in that carpet, after they cleaned it and everything, they couldn't get it all because it's at the subfloor or whatever, they're going to put it in a big pile somewhere, and it's going to rain, and it's going to dissolve, and all of us going back out of the ocean as it's done, or be subducted back into some sort of geologic formation and eventually come up again and be released as it has done. I mean, the whole mountain ranges have come and gone on this planet that we don't even know about. Came and went. And if you want to go see those ancient mountain ranges that no longer exist on this planet, just go to the ocean and just reach down and taste the salts, and then lift up the sand. And what the sand is are these, oh my God. Really, soul's truth. What sand is silicon dioxide. And it's the most resistant to weathering or dissolution of all the crystals, silicon dioxide. And that's what sand is. And so in this rock are these little white crystals in here that are silicon dioxide. And the little dark crystals that are in here, actually the dark crystals typically have the important mineral nutrients for life. And so the darker the minerals are, the darker the rocks are, usually the better, quote unquote, better the soils are that form from them. So different soils form from different kinds of rocks. And different kinds of soils have different properties that can support different kinds of plants, and that's what native plants are. They're the plants that are adapted to the geology and the climate that's there. Because some of these rocks just don't have the mineral nutrients that are required by others, right? See what I'm saying? What's the answer? Wow, who said that? All right, down here. All right, gold star. First gold star coming out today. Yeah. Oh, I won't put it on your sign. This will get you a free drink at the bar later. Somebody buy that guy a drink, all right? Look at him, I got him right here. I know why you came. See, used be damned. That's bullshit. This is a gold star right here, all right? So, thanks. What was the answer? What's the answer? Add organic matter. I mean, think about it. Look, there's a hole here and a hole here, and there's a tube going through your body. And that is the external world that's going through you, right? It's not in your body, it's going through your body. And inside there, inside that, your gut, are the same bacteria and fungi that are in the soil that decompose organic matter. And so you put it in here, chew it up, increase the surface area, deliver it to a bunch of microbes that live in your gut, and they ooze out enzymes that dissolve the organic matter. And then it goes into your bloodstream, and that's why you're here. And some of that is mineral nutrients. Inside of your body right now is a giant secondary mineral made out of calcium in the shape of a human skeleton that's holding up this giant macroorganism that you are a habitat. I mean, inside the hair follicles in your eyelashes are nematodes. There's amoeba that live down in the gums of your mouth that are waiting for you to go to sleep, and they climb up at night and they eat the protein deposits off of your teeth. I mean, 80% of your body by dry mass isn't even made from human DNA. You are a habitat. You're a four-dimensional complex habitat, a self-organized natural body, a living thing. Same thing as what soil is, a four-dimensional complex habitat, a self-organized natural body, a living thing. I would argue you are soil now. You're made of exactly the same things, same functions. It's all happening. Adding organic matter, right? That's how it works. Think about that. I dare you to just not think about that when you're laying in bed at night, all alone. And you're just laying there going, I am soil. And I belong to this earth. And it's a fact. And it won't be long now. And it will truly be the fact of life and the rest of it. So what soil is our dissolved minerals. And when that rock falls apart, there's different size particles of sand, silt, and clay. Sand is anything from 2 millimeters down to 0.05 millimeters. Silt is anything 0.05 millimeters down to 0.002 millimeters. Anything smaller than 0.002 millimeters is considered clay-sized particles. And the texture of that rock determines the texture of the soil in the size of these crystals, right? So different coarse-textured rocks become coarse-textured soils, etc. And the types of minerals that are dissolving determine the chemical environment, which begets the biological environment, etc. You kind of see where I'm going with that, right? So, and soil self-organizes into horizons where the surface soils are darker than the subsoils. And we'll talk about that. And that's because of this whole other thing we have to talk about before we can even start this slideshow, okay? And that is organic matter. What's the answer? Make sure you get the add organic matter, okay? Because of what organic matter is. What organic matter is, look, I have a stir stick here from my coffee. This was once a tree. Come on, nothing? I don't get nothing for that? This was once a tree. One more time. Was this once a tree? Yeah. Okay, thank you. And probably a beechwood tree. Who knows? Isn't that what mostly these are? Yeah. Just made that shit up. Anyway. And what is a tree? What is a tree made out of? Organic matter. Wood, organic matter. What is organic matter made out of? Almost always the right answer, soil, rocks, but mostly what is this? Cellulose, who done that? Yeah, okay. Hold on for your gold star. What is cellulose made out of? Carbon, he said it, man. Carbon, all right, you get a gold star for that. Actually, you got to start seeing soil bumper sticker for that. Maybe the only reason to have a car is to have this bumper sticker. Start seeing soil. I say start being soil. leave the start off. Just be soil. Or you are soil. Whatevs. Nice, right? So, what is organic matter made out of? Carbohydrates, which is made of carbon mostly. I mean, mostly in living trees, of course, a lot of water, but if you drive off all the water, this is mostly, we are carbon-based life forms, right? And where did the carbon come from? This is the whole, we talked about the mineral side. Now we're going to talk about the because soil is, basically, it's minerals of different sizes and types, organic matter, and then the rest is space. Like mostly, it's the empty space. Where the soil isn't is where the soil, where the activity in soil is happening. Nothing happens inside of a rock. It happens in between the rocks. That's where the pores are. That's where the water is. That's where the air is. That's where the roots are. That's where the nutrients are. That's where the bacteria, the fungi are. That's where everything happens, is in the pores. And the pore size distribution, the size of the pores, is determined by the particle size distribution, sand, silt, and clay. And the different particle size distribution creates a different pore size distribution, and small pores hold water against the force of gravity, and large pores drain under the force of gravity. And there's your two habitats right there, right? One, water. So small pores hold water against the force of gravity because of the force of adhesion and cohesion, capillary force. And when you're taking a shower today, can I use that water again? I promise I'm not really touching it, but you've all done this. You've all taken a bath or a shower and said, what the hell is going on? That little bridge of water, look at that back row. See that back there? You know, guy comes and says, look at my fingers. Anyway, there's a little bridge of water. It's like, how is that happening? Because of capillary force. Small pores hold water against the force of gravity. Large pores drain into the force of gravity. In fact, the difference between a micropore and a macropore is 0.08 millimeters. If it's smaller than 0.08 millimeters, it tends to hold water against the force of gravity. And the smaller it is, the tighter it holds the water because of capillary force. And anything larger than 0.08 millimeters drains. And when it drains, imagine a wormhole, a connected pore made by an organism, right? And now a raindrop goes down into there, pulled down by the force of gravity. That single raindrop, as it gets pulled down, what's being pulled in behind it? No? Huh? Air. Who said air? All right. Too many golds. What the hell am I doing here? Let's give out some gold stars. So when that goes down, I guess I'll get you a free drink at the bar later. Okay. So when the soil is draining, the soil is breathing. And when do plants need water at their roots? All the time. And when do plants need air at their roots? All the time. And that's why you want a wide pore size distribution in your soil for the plants to live. Because they breathe at their roots. They breathe oxygen at their roots. But quickly back to what this is made out of, carbon. And where does the carbon come from to make a tree? From the atmosphere, right? All right. I want to waste. This is not wasting time. I'm out of gold stars. We're moving to green stars.
Oh, yeah.
Which that gives you 2 shots of vodka at the bar. Okay. So, see you later. Huh? What? No, I give out the stars, but okay. All right. How about a star for everybody? And we'll just call it even. Yeah, man. Oh, you want to come over here? Yeah, where do you want that? Oh, wow, look at that nice drawing. Can I put it right up there?
She said air.
All right. So it comes from the air in the form of carbon dioxide, right? The thing that's invisible that nobody believed in until about 100 years ago or something, right? Okay, so this is made out of carbon dioxide. Now, most people in this room, and most people like, oh yeah, plants, they like breathe carbon dioxide and they exhale oxygen. It's like, no, Plants don't breathe the atmosphere. Plants eat the atmosphere. They eat the carbon dioxide to build their tissues. This is concentrated carbon in the form of carbon-to-carbon bonds, carbohydrate, that came from the atmosphere from a gas called CO2. And CO2, in order to make this, the plants, they take in the carbon dioxide, and then they take it apart, and then they put it in together into these tissues. And these tissues include the trunk, the leaves, the seeds, the roots, all the different parts of a plant. They're mostly made out of carbon that was taken apart and put together by some sort of force. I mean, that's work to do that. It doesn't just happen passively. And in order to do work, it requires energy. And where does the energy come from, think trees? Say it again. The sun. 93 million miles away, there's a star that's giving us tiny little sliver of that energy is hitting this little planet. And plants have figured out a way to use the energy of the sun to tear apart the atmosphere to build their tissues above and below ground. And in this carbon-to-carbon, these carbon-to-carbon bonds that make up this thing, it's really strong. It's kind of an amazing material. And in this right now, this piece of wood is the energy of the sun at the time of photosynthesis. It's in here. Photon comes from 93 million miles away, hits chloroplasts, excites an electron into a higher orbital, drops down. That energy is captured in an ATP molecule, which is the energy molecule, which can go anywhere in the cell, anywhere in the body, based on the instruction from the DNA, which itself is made from dissolved rocks, the coded information. And then, then that energy is released to rip apart CO2 and then blown apart to make this. And in here is that energy stored as chemical energy from the sun in here. And in fact, small demo here. I'll come over here because I've been neglecting you guys. Sorry. Hey, way over there, I'm taking out a tiny piece of wood. Yeah, this is from Brazil. I got these matches in Brazil. So this is grown in the tropics. Probably not. It was just made in Brazil. It's probably beechwood from China or something, but whatever. And this was once a tree. And this is made from carbon that came from the atmosphere when the plant ate the atmosphere, and the energy of the sun is inside it. If I get this to 451 degrees, you know what happens to it? It oxidizes. The oxidation chemical reaction that we call burning is an oxidation chemistry. And the building of these tissues is reduction chemistry. This is a redox. The plants growing, plants are the mother of all redox reactions. Because in that is contained the energy of the sun. When I get to 451 degrees, that's oxidation. That is the energy of the sun. Right there, right now, and it's giving off heat. Yow. Okay? That energy, that light, was the energy that was captured from 93 million miles away by a plant that lived in soil. And if I, was in my classroom, we'd burn a bunch of paper right now outside. And this, didn't completely combust because it's not the perfect burning environment, but I could light this, say this book on fire. Watch this. Just kidding. And this was once a tree. I mean, what is a book? A book is a piece of wood that you look at and you have a psychedelic experience. Crazy world. And what's happening in your mind that you can have the psychedelic experience is all from energy from the sun that was captured by photosynthesis. The plants that lived in soil, and then you ate the plant or you ate the animal, or your mom did, and that's how you got the energy. That's why you eat, is to get the energy from the sun, right? Every blink of your eye, every beat of your heart is energy that came from the sun. You're just a big bag of wet rocks. You're not even a human. You are habitat. I would say you are soil. It's almost over. And you're an expression of sunlight energy. Well, that's what you are. And when we burn this, if we were to burn, think about it. In a fireplace, you burn wood, you throw it in there, you keep throwing it in there, and where does the wood go? It goes away, right? It magically sort of disappears. Where is it going back to? Back to the atmosphere as CO2 gas. And the energy that's coming off of there is the energy from the sun that's being released, an exothermic chemical reaction. This growth is an endothermic chemical reaction called reduction, and oxidation is the opposite. And there's also some water that's released that you can't really see unless it's really dry and cold, like in Minnesota where I'm from. You see steam coming out of tailpipes of cars and out of fireplaces. And what's left over after the fire is out in the fireplace? Ash. And what is ash? No, carbon goes back to CO2. Minerals. Those are the minerals that were dissolved and taken up by the plant. That's what ash, rocks don't burn, minerals don't burn. That's why we build fireplaces out of minerals. That's why we put a circle of rocks around when we're at the campsite, is to keep the fire from spreading because it doesn't burn. And what's left over is the ash, and the ash are the mineral nutrients that were dissolved out of the rock and taken up by the plant. That's the phosphorus, the potassium, all, the sulfur, everything that was taken up by this plant to do all the things that needed to be done to build the plant. The phosphorus from the DNA, all that stuff is left behind. And that's what fertilizer is. And that's why after a burn, it's like fertilizing. Right? That's why they burn fields historically in Oregon, where I live, is to release mineral nutrients that were mined deeper down where the roots went, brought them to the surface. That's what cover crops do. You put them in and you get nutrients from below, you bring them up to the top, and you cut them down, and then they rot. Now, I mean, think about it. How do you get a fire to burn hotter? Add oxygen. Okay, everybody, you ready? Together. Oxygen in. CO2 water vapor heat out. Oxygen in. CO2 water vapor heat out. What's left over? Mineral nutrient ash that goes into your body and via the bloodstream that reassembles the skeleton inside of you. That's what the ash does in you. It builds your tissues. It builds your DNA. It builds the phospholipid bilayer in every cell in your body. And how do you get that to happen? You eat food, and what do? You mostly are, when you're eating food at lunch today, adding organic matter in this hole. When you're doing that, what you're doing is you're adding carbon and energy and mineral nutrients. And 2/3 of the carbon that you're eating will be respirated as CO2. 1/3 of it will be incorporated into your body tissues. And so you can eat, that's why you eat. All right? So that's what organic matter is. And so soil is mostly minerals, about half of it's minerals, and a little bit of it is this organic matter that contains energy of the sun, and then the rest is space that's either filled with air or water. And that's the fundamentals of what soil is. We're going to talk about how it works, but we had to do all of that first before we could talk about, and my first slide, okay? Hey everybody, my name is James Cassidy. I'm here from Oregon State University, and I teach a bunch of soil science classes. All right, so here's my first slide. You ready? Soil, all right? That's what all that was. Okay, what soil is, right? And we have to talk, I mean, there's a million things we could talk about, but first of all, I just want you to understand that there are different soils in different places because there's different amounts of water and different kinds of rocks. I don't know if you know this, but there's over 20,000 different named soils in the USDA system, and there's other systems. There's 7 major systems of soil taxonomy, just like plants and animals, just like trees. And the FAO system has 26 soil orders, blah, blah, blah. But the USDA system that we currently use has 12 soil orders. And that means any soil you'll ever see here, anywhere in the world, belongs to one of the 12 soil orders. And I kind of picked out a couple. And the 20,000 different soils, like there's thousands of different kinds, or hundreds of different kinds of mollisols, and there's hundreds of different kinds of iridosols, but these are the 12 soil orders. I just wanted to show 2 of them. And if you look on the left, what that is what's called a soil profile. And if you dug a hole and you looked at the wall of it, right? So that's a horizontal presentation at depth. There's the surface, and you're looking down maybe like 4 or 5 feet or something like that, right? A road cut. And on the left is called an iridosol. And what do you think iridosol means? Dry. Do rocks dissolve in air? No, they dissolve in water, right? So there's actually a lot of iridosols right around this place. Even though there's a river here, it's been through here, but it's pretty dry. And an iridosol has no water during the growing season. There's a whole, there's a whole taxonomy to this. But here's a dry soil, so it doesn't get very much water. So are there a lot of nutrients being released? Not really, right? So, and without nutrients, is there a lot of carbon being captured from the atmosphere and energy from the sun? Probably not, right? Because the nutrients are sort of the basis of biology for them to be able to eat the atmosphere and get energy from the sun. So what you're looking at right here, this top layer, I get way down there, we can see that? That little top layer right there, that's about 1 foot thick. That's the soil. And that's it. 1 foot is the entire, that's the habitat for anything that's going to grow there. And looking at that other picture of that tree, it couldn't live here. Not enough soil. Not enough nutrients to build a big tree, right? And look at the color of this soil surface. I mean, and what this is about 12 inches. What I can tell you about that, soil is about 50% porosity. So for water to travel 12 inches deep in a medium that's 50% occupied, how much water annually falls there? About 6 inches. So the average precipitation in this soil here is about 6 inches, which goes down about 1 foot. And then it stops raining. And what's the first thing to dissolve out of soil, out of a rock? Salt. Yeah, the salts travel down and they get right about here and they stop. And then they dry out. And that keeps happening over and over and over and over. And 10,000, 100,000 years, now you've got a salt crust right here. The water never gets to the water table, to the river, to the ocean. It doesn't rain enough for that to happen. And so you get this hard, this pan, salt pan here. And that's salty. And salts affect the osmotic gradient and all that stuff. And plants that aren't adapted to having lots of salt around them don't live there. And below that is just the rock from which the soil originally formed. But it doesn't ever get wet because there's a salt layer now. Even if it does rain more there, it's impenetrable with the water. So it's all going to wash off, or something's going to, it's not going to be ever restored, quote unquote. So if you want to live there, you got to look like that. Right? And that's what's adapted to living there. It's something that can handle hot, dry, salty, not too much. And look at the color of the soil. There's not a lot of organic matter being produced, so there's not a lot of carbon and energy in the soil. What soil is a battery that stores energy from the sun in the form of carbohydrate. And that's organic matter. And what's the answer? What's the answer? When you add organic matter, what are you adding? You're adding carbon from the atmosphere and energy from the sun to feed the billions in a single pinch. And you're thinking, so what's happening when in a compost pile? Think about a compost pile. A compost pile is a bunch of organic matter you add water to, and you notice how it goes away? It's going back to CO2, water vapor, and heat. That's the energy that makes it hot, that kills the weed seeds and the pathogens. And when that pile of compost is reduced down to about a quarter of what it was, the mineral nutrients are more highly concentrated in it because there's ash in it, right? But it's not at 451 degrees, right? It's happening at about, I don't know, between 90 and 104 degrees or something like that, 140 degrees, right? Same thing is happening in you right now. You add food, you don't get to 451 degrees. So what are the bacteria and the fungi doing? They're oozing out chemicals that are called enzymes. And enzymes are catalysts. And those catalysts allow for the oxidation chemical reaction called burning to happen at 97.5 degrees. Or maybe not so much, maybe even colder than that, at 54 degrees. They ooze out these enzymes because in order to get something to burn, you got to get to 451 degrees, wood does, and you got to shake the molecules enough that they happen to align in a certain way where that chemical reaction happens, where the CO2 is produced and energy is released, right? And an enzyme is just a chemical that goes, hey, what if we take this molecule and get it closer to that one? Boom, and it happens at a lower temperature. So the activation energy, in order to get the oxidation reaction called burning to happen, the activation energy is lowered by chemistry, by biota. The billions in a single pinch, that's what they're doing in the soil. That's what they're doing in your gut right now. They're oozing out enzymes from the food you ate, and they're dissolving it and releasing carbon dioxide, CO2, water vapor, and heat. Just put your hand in front of your mouth and go on it. You feel that heat? That's the energy of the sun that was in the food that you ate. And that's what's happening. And that's not happening very fast or very much in this soil. Where on the right-hand side, we have mollisols. And mollisols are like, this is like soil porn here, if you're a farmer. And what this is in feet. I mean, 2 feet. Look how dark it is. You know why it's dark? A lot of organic matter. And how did it get there? Roots, grasses, which inject carbon, energy, and mineral nutrients into the soil. They live and die, 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 they live and die for 20 million years, and that's what mollisols are. And there's a lot of carbon, a lot of energy, and a lot of mined nutrients there. In consort formerly with grazing animals like bison and stuff. And that's what the mollisols in the middle of the country, in the center of the kind of Mississippi Valley and stuff. And so this is like amazing agricultural soil, mollisols. And so, I mean, like a third of the Earth's ice-free surface is either iridosols or inceptisols. 1/3 of the Earth's ice-free surface isn't really appropriate for agriculture, probably for the trees can grow in any of these because they're adapted to, because they're native plants are adapted to these different soils, and whole ecosystems are adapted to these conditions that produce these soils. I mean, here's a map of the global soil regions. And I want you to look for the mollisols here. And they're shown in green on the key. And 21% of the United States land mass area is mollisols. 21%. Worldwide, it's 7%. That's all you need to know about why you're just hanging out here today playing hooky and just hanging out and staying at a hotel or whatever and learning about trees and have a job and all that stuff, because we have more mollisols than almost any other country on the planet. I don't know if you can see the other area where the most mollisols are in the world. Right up here, Mother Russia. I mean, what do you think the Cold War was all about? I mean, they who have the advanced agriculture, because they have the good soil, have the advanced technologies, and that includes thermonuclear weapons. And that's who controls the planet, is they who have the soils. And how do they get those soils? The old-fashioned way, right? Take them. War, whatever, right? Because power begets power. And I don't know if you know where Ukraine is located, but it's right there. Can you see that right there? Ukraine. 80% of Ukraine's landmass is mollisols. What do you think the hot war is all about? I mean, this is fundamental stuff. This is what this is. And look at where the iridosols are. Right here. These are the troubled spots in the world, right? Because the basic resource isn't there. And so what you're really looking at here is a map of political power. And where the good soils are, or where the political power is. And I would wonder if our leaders even have any idea where the political power comes from. I'm just telling you. It comes from soil. Okay? And preserving the soil and caring for the soil is a national security issue. And it was seen, there was a whole time in the prehistory times here in America where a president said, we are going to protect the soils, and they created the Soil Conservation Service because of the Dust Bowl in the 1930s. And that begat the Natural Resource Conservation Service, and that's why we mapped the soils in the country. And we actually applied the knowledge of how soils form to make maps of where the soil is so that we would know which ones are good for this and not good for that, and which ones are sensitive, which ones we have to take care of, which ones are vulnerable, all that stuff. I mean, that's why you're here. That's why this town is here. I think it's mostly because there's a lot of oil here, isn't that true? And what is oil? Carbon-to-carbon bonds. Where did it come from? Photosynthate. What comes out of the tailpipe of a car? CO2, water vapor, heat, and ash. And what does it produce? Energy. And what does the energy do? It heats up the air inside the combustion chamber, which expands it, which pushes the piston down, makes the crank go around, and that's how you got here, is ancient photosynthetic production during the Carboniferous period. The Carboniferous period was a time on this planet when there was all this vegetation, but there weren't any fungi yet to decompose it. So it just piled up miles high, dead stuff. And then it got subducted, and under high pressure and high temperature, it became crude oil. And that's why when we burn it, CO2 goes in the atmosphere. Right? And then the smoke comes out, that's the ash. So, and these are the frozen soils up in the northern, the high latitudes rather. And those are mostly organic matter soils. In fact, I don't know if you can see these little brown spots kind of up in northern Canada. If you look over here. Those are the peat bogs. That's where organic matter is produced, mosses mostly, so much of it, but it's so cold and wet in the winter that it doesn't really decompose. And it just accumulates. It grows, dies, doesn't decompose. Grows, dies, doesn't decompose. Grows, dies, and pretty soon it's like, 100 feet, 200 feet thick moss, sphagnum peat moss. And that's what comes in the bag when you buy, quote unquote, soil, which isn't soil, it's just porous media that's made out of sphagnum peat moss. And you'll notice that brown stuff kind of ends at a certain point and becomes blue. That's because it's frozen. And that's called a gelisol, like gelato. And gelisols are soils that have a permafrost layer somewhere in them. They're always frozen. They may thaw in the summer, the little bit of summer they have, but below, you go down a couple feet, it's frozen hard. And for every, and that's mostly histosols, which are these sphagnum peat moss soils. And for every increase in temperature by 10 degrees in soil, there's a doubling of biological activity. And if we were to double our biological activity in this room, the CO2 levels would increase in here from the food that we ate. And so when these start to thaw, there's more CO2 being produced. Just saying. Figure it out. And here's the tropics. You may think, oh, aren't the tropics good? Actually, no. Who's been to the tropics? Look at these people. We fly around in murder tubes for fun and just spewing CO2 because we live in a place where there's more. You know what it feels like to be in the middle of a global soil crisis? Like this, if you're us. If you live in a place where there's more mollisols, you know, this is coffee for all, you know, whatever, donuts, you know, whatevs, healthcare plans and insurance and cars and second homes and all that jazz. So, but in the tropics, they're mostly red, yellow, purple, white soils because what they mostly are is iron oxide and aluminum oxide. That's what remains. After a rock completely dissolves away, the only thing that really remains are these oxides. And so where are all the nutrients in the tropics? They're all in the ocean. And you're saying, well, what about the jungle and all that stuff and the diversity above ground? That's because they're all scrambling to hang on to the nutrients. So the diversity of organisms is very high above ground because there's not much below ground habitat. So the minute a leaf falls in the tropics, before it hits the ground, it's being ripped apart by some ants. Before the ants go to bed, they're being eaten by something else and shot out right on the roots on the surface of it, where the trees just take it right back up. So it's being cycled, all the chemical energy, mineral nutrients, and all that is being cycled above the soil in the tropics. And as you move to higher latitudes, that cycling goes deeper underground to the point where it's all underground. And right where I live, in the kind of this 45th parallel, where these mollisols are, that's right where there's a lot of above and below ground biomass. Which is why there's these giant forests and stuff in the Pacific Northwest. Anyway, just wanted to get your head around that. I don't know where we're at. I think we're done, right? For the moment. And then you're coming back for part 2. And we're really going to dig in. We're really going to school after this. So you better have a cup of coffee, add some organic matter, and come back in 5 minutes or something so we can keep on time here. Cool. All right. See you then. Oh, yeah.